Our project is being sponsored by UTRC, also known as United Technology Research Center. They are the research division for UTC. They have 5 locations worldwide with around 600 employees, located in Berkeley, East Hartford, Ireland, Italy, and China. They specialize in aerospace and commercial buildings, as well as other technology initiatives. They look to better the companies seen below, such as Pratt& Whitney, Collins Aerospace, Carrier, and Otis, and to a large extent the whole world through technology innovation. The problem we are tasked with solving is creating a test rig to model two-dimensional low-amplitude, high-frequency wear on a specimen over a long period of time. Mechanical parts in an aircraft withstand high-frequency vibration over any given flight not proportional to the wear that they undergo in their normal operation in other applications. More simply put, they wear and fail sooner than in other applications. Currently, the method being used at the testing facility at UTRC is a linear actuator that can only test wear in one direction at only around 300 Hz. Picture to the right is a linear actuator that's testing in only one direction and is currently only testing at 300 Hz at the facility. This right here is not the best method for testing wear, as it's not an accurate way to model wear that occurs in the real world. So we are tasked with designing a test rig that's capable of two-dimensional wear in both the X and Y direction, and with a goal of 1000 Hz mechanical wear overall. This brings us to our project deliverables. The purpose of this project is to develop a method of simulating different frictional patterns between two given surfaces at varying levels of frequency and amplitude. So we chose to go with a magnetic bearing-based design, coming to the conclusion that it will be capable of testing wear of up to 1000 Hz. Pictured right is a magnetic bearing given to us by our sponsor. We would use this to test our project moving forward, as well as to toy with it to get a better feel on how it works early on. Below that is an early model of our bearing and how we would possibly set it up for testing. We would also control the system by driving current into the bearing coils through amplifiers given to us by our sponsor, thus creating a magnetic field within the bearing itself. And with this design, another good thing is that we will be able to make future improvements going forward, which is very good because if we had a snag in our testing, we could easily go back and try to fix it and find it without having to scrap the entire project itself. Pictured here is a magnetic bearing we have been tasked to test for our design. Using this method, we look to provide our sponsor with a two-dimensional testing rig capable of vibrational wear of up to 1000 Hz at an amplitude of just 0.25 millimeters. So the general function of a magnetic bearing is to keep an interior object at the center. However, for our purposes, the bearing will be used to keep an object off-center to be able to induce the needed wear patterns to be simulated. To accomplish this, we have developed the necessary hardware circuit as well as a LabVIEW control GUI to manipulate the given signal to the coils of the magnetic bearing, which Matt will talk about a little later. However, this causes a change in the produced magnetic field from one cartridge to the other, causing a movement of our interior core piece. Here we have the bearing attached to a fixed platform in the middle, and we have the core that will be using will have attached a platform to that for use of specimen. We will run the current through the magnetic bearing and the coils of the magnetic bearing to then create a magnetic field within the bearing, and then have create vibrations within our core that will then lead up to the specimen and create vibrational wear on the specimen. The fixture also allows for a variable load to be applied from above to further adjust the rate of wear between the specimens. Picture here is a further development of our model. The 4 black boxes on the side are where we will be housing our amplifiers, and the crown on top of our magnetic bearing surrounding the housing unit. That is where we will be using the variable load to be applied from above. Data gathering equipment are also located on a test fixture. Those are located on the X and Y axis as seen to the side on our model. And this will be used, we will be using non-contact displacement sensors on the X and Y axis of the bearing to further visualize and record accurate movement of the movable interior core to verify the accuracy of how the input signal translates to mechanical frequency and wear patterns.
This is the schematic for the circuitry used to drive our magnetic bearing. Shown on the left is a zoomed-in schematic of what drives one individual quadrant, which is essentially the same for all 4 quadrants, with a change only in the biasing. To drive our bearing quadrants, what we did was power our amplifiers with a voltage source of 65 volts and drive a signal through LabVIEW, interface that with a sound card, send that through an audio transformer, and use that as a reference on our amplifier in order to send the correct signal to our bearing quadrant. To drive our bearing, we used a program in LabVIEW that we built in order to determine what signal we could output. This is the front panel of one of those programs with options for frequency and phase shift, which can allow us to create a circular pattern or an elliptical pattern in our output. Shown here is the block diagram of that same LabVIEW program we built. This video is a demonstration of us driving our magnetic bearing and iron core with our LabVIEW program. Near the end of the video, you can see a stopped oscilloscope screen showing two waveforms that are 90 degrees out of phase. These were taken from position sensors measuring the position of our moving core. This indicates that we were successfully able to create circular motion in our core.